Let me tell you it. I think maybe a good starting point would be, let's review a little bit about capacitance. Let's hit capacitance from the beginning, not beginning, but brief review of what capacitors are. And then from there, I want to tell a story about energy inside a capacitor. I think I'm going to shuffle around the order a smidge. My 3 o'clock section took longer than expected on one of the problems, and that shuffled the order a bit. So I think we're going to go in reverse order. You need to do both of these things. You need to be able to apply both of these concepts: energy in a capacitor if you're free, and energy in a capacitor if you are the capacitor. We'll do this in the reverse order. First, though, what the heck is a capacitor? What do you need to know about capacitance? What hopefully is review about a capacitor. Here's my review of capacitance. Please tell me this is review. The starting point that I would derive if this were a calculus class, but I can't derive because we don't have calculus in here. This is algebra based. Is that electric field inside a capacitor is, very importantly, not KQ1R squared. KQ1R squared is for a free charge. If you've got them smeared out over the plates of a capacitor, KQ1R squared turns into Q over A epsilon. A is the area of the plates, Q is the charge on the plates. The electric field inside the capacitor is simple. It's just really the charge density divided by a constant. Okay, so if we know that the electric field on the capacitor plates, between the plates of the capacitor, has an equation, then I can plug this into the equation voltage equals electric field times distance. Where'd that minus sign go? Excuse me. As I alluded to last time, I don't usually care if I'm using a capacitor as a device. I don't usually care about the direction of the electric field inside. The electric field is always going to point from the plus side to the minus side inside the capacitor. And I don't really see the electric field inside the plates of the capacitor, so screw it. I'm going to drop the sign that tells us that the voltage is going up or down in the direction or opposite the direction of the field lines. That's extraneous from the point of view of using the capacitor. So I'm just going to say voltage magnitude equals electric field times distance between. Okay, I take this equation, I shove it into this equation. Delta X, the distance along the field direction, the distance from plus to minus in a capacitor is usually given the letter D. So I turn E delta X into Q over A epsilon naught D. I'm just plugging one equation into the other. Now look, and think for a hot second about this. What is the nature of a capacitor? What is the nature of the voltage versus charge in the capacitor? Voltage, electrical, charge, electrical, everything else, size and shape of the capacitor. This says that if I've got a parallel plate capacitor, the voltage is directly proportional to the charge. If I change the charge, I change the voltage. If I change the voltage, I change the charge on the capacitor. Everything else just stays the same unless I physically modify the capacitor. If I pull the plates apart, if I change the area, then I'm modifying the capacitor. But a normal capacitor is just like this encapsulated little blob that electronic component that you use. These D, A, epsilon's a constant, don't change. So how do you change the capacitance of a capacitor? You change the size and shape. Once you have a capacitor of a given capacitance, then there's a constant ratio of voltage and charge to each other. Know that, write that down, think about that. Here is the meaning of capacitance. Voltage and charge are directly proportional. The capacitance of that capacitor is A epsilon naught over D. But I'm defining capacitance as the constant in proportionality between charge and voltage. This is always true. This is a definition. This is mathematically, this is a matter of logic. You can't have a capacitor without this being true. There are kinds of capacitors that have a different equation for capacitance. they always go back to the size, shape, and materials of the capacitor, just like a resistor has size, shape of the resistor, and materials of the resistor make up its resistance. This is true for a particular capacitor. If I want to know how much capacitance a capacitor has, I can use this formula to find out how much capacitance it has. Once I know how much capacitance the capacitor has, I know how the relationship between charge and voltage is going to go. This makes a capacitor have a capacitance. Once I know the capacitance, charge and voltage relate to each other. Make you sensing? Context is everything, baby. Jane, please. Yes, I am. Thank you for a reminder. Always true? True in particular circumstance. I'm only going to give you parallel plate capacitors, but and for a parallel plate capacitor, that's a true statement, but I'm going to be testing you on what is an always true equation, what is a definitional equation, what is the defining equation for this, that, or the other concept, and what is true for a particular kind of thing. I really want you to be able to distinguish these ideas from each other. Okay, gut feeling. A capacitor is like a storage tank. It's like an air tank for a diver. It's like a balloon. It stores charge, just like an air tank stores air. Your mental picture for what capacitance is. Capacitance is like the size and shape of an air tank. Please note, capacitance is not capacity. Capacitance is not the amount of charge the capacitor can get. Capacitance, farads, is not the same thing as coulombs, charge. Capacitance tells us how easy is it to pack the air tank, to pack the capacitor with charges. The bigger the capacitor you have, capacitance of the capacitor you have, the easier it is to store a lot of charge on its plates. Okay, I just made this point. No. One more thing on point 2. The easier it is to store charge on the plates of the capacitor, the bigger the capacitance you have. Everyone is 800 PV equals nRT in class, right? Pressure, what is it? How much the stuff doesn't like to be packed in, right? The energy, if you will, that the air has to re-expand, that's voltage, man. Pressure is voltage. N, what's N? In PV equals nRT, the number of moles of air, the amount of stuff packed in, that's charge. That's just like Q. In this example, the volume of the air tank, PV equals nRT, the V in that, that's capacitance. The bigger the air tank you've got, the more air you can pump on before the pressure gets to a certain level. And it's different than the amount of air in the air tank. You could always have more or less pressure put on. A bigger or a smaller air tank is going to, well, you could always pump more air in, assuming that you don't burst the sucker. There's no absolute maximum capacity of air. So you get to a bursting point, you can always pump more on. So capacitance and capacity are not the same thing. Just like the volume of air, I'm sorry, the number of moles in a storage tank is not a fixed quantity. Okay, I'm going to, since I already talked about the defining equation for capacitance that's always true and how we make a given capacitor, and skim over this. No, hold on, wait. Please turn to each other. This is a very important point, and there's some subtlety to it. Please turn to each other and tell each other, when would I use this equation? When would I use this equation? What is always true? What is sometimes true? When I know this, what do I know? Ready, set, go. It's a meaning. One on the right, I guess when you're given, you don't know what you've done. However, they're on the other. Right here, get your right here. Yeah, let's bring it together. If I pump up an air tank, does it get bigger? If I put more pressure on a scuba diver's tank, does the volume increase? No. If I increase the charge on the capacitor, does the capacitance increase? No. If I increase the charge on the capacitor, the voltage goes up. Just because you have an equation, Q equals CV, C equals Q over V, you don't know which of these two quantities this controls without thinking about the meaning. If I increase the charge on a given capacitor, the capacitance of the capacitor doesn't change. The capacitance of the capacitor is controlled by its dimensions. Unless I change the physical dimensions of the capacitor, its capacitance can't change. Please. Voltage does not change in a battery. Capacitors are not batteries. A capacitor is a tank. A resistor is a sponge. A wire is a tube. And a battery is an air pump. We can? It's source and charge. I mean, in particular, the starting point for understanding where the most popular use for a capacitor in the world might be is if you've got a power supply, it's got some rippling voltage on it, the voltage is not staying constant. You put a big hunk of capacitor there, it's going to smooth out the ripples. It'll act as a storage tank, and if the applied pressure goes up, it'll absorb that pressure. If the applied pressure goes down, it will release some of its internal charge. Good. So the pump, the source of energy, batteries, wall outlets, power supplies, whatever. Capacitors, something that stores charge. And for our purposes, we're not yet talking so much about how they act in circuits. We're talking about them in order to get a better idea of what type of voltage, field, and charge are. That's what I'm applying this in here. That's what I'm applying this to. Without capacitors, we've just got voltage equals K2 on R, electric field K2 on R squared. These formulas are very hard to manipulate because they depend on position. With the capacitor, the electric field formula is very simple, so I can get down into the relationship between voltage and field without calculus. So I guess it's twofold. What do we do in a circuit? Well, it smooths ripples. What do I do in physics 112? I understand the relationship between two quantities. Okay. Google question A, tell me, how can I double the capacitance of a capacitor? If you think the answer choices are all of the above, put 1, 2, 3, 4. If you think the answer choices are just 1 and 3, type 1 and 3. Google question A, tell me what you think would change or would double the capacitance of a capacitor. I just said this. Good, let's see. Good salute. Okay. Again, let me go back to my analogy. How do you make a bigger air tank or a diver? The scuba diver, I want a bigger air tank. Do I change the pressure in the air tank? Will that change the size of the air tank? No, you have to build a bigger air tank. If I increase or decrease the voltage, if I decrease or increase the charge, that doesn't affect the size of the capacitor. You have to physically modify the capacitor. The correct answer is 3 and 4. If I increase the charge on the capacitor, the voltage will increase. If I increase the voltage on the capacitor, the charge will increase. The capacitance of the capacitor is fixed by the capacitor size, shape, and ultimately material, although we don't go into that in 112, how material affects capacitors. The correct answer here is, in general, to change the capacitance of a capacitor, you have to change the capacitor, not the electricity applied to it. Okay, so follow-up question here. How do I change the resistance of a resistor? Question B. How do I change the resistance of a resistor? I'm seeing true statements about resistance, but you're not answering the question. What do I do to change a given resistor's resistance? I've got a 100 ohm resistor. I want a 200 ohm resistor. What do I change? You don't have to remember the exact equation. Good, good. Bad, good. Let me go back to the previous slide here. A resistor's resistance comes from its material size and shape. The resistivity, the length of the resistor, the cross-sectional area of the resistor. These control the resistance of a resistor. If I want to change the resistor, if I want to change the resistance, I have to change the resistor. The voltage on the resistor does not control the resistance of the resistor. The voltage across the resistor controls the current through the resistor, but the resistance of the resistor is a property of the resistor. So in exactly the same way with capacitors and resistors, capacitance, resistance, these are properties of the capacitor, of the resistor. Once you know the value of capacitance or resistance, you know how voltage affects current. You know how charge affects voltage. But changing the electricity doesn't change the capacitor. Changing the electricity doesn't change the resistor. Write that down. Take a note to yourself. This is an important point. And turn to your classmate and express, what is the big idea I'm giving here? What controls what? What affects what? They're dead?
Well, just like I have no.
Oh. So what is he? Chopped liver? Okay, question time. Question me. Nadie? Nichts? Please.
So resistance and capacitance, they have, if you wanna change them, it's the same thing essentially?
Yeah.
Okay. Like using the same thing, changing the material, I guess, the length of it?
Yeah.
Okay.
Later we'll meet a component called the inductor. And you'll never believe this, but to change the inductance, you have to change the inductor. The inductor connects voltage across the inductor with something about current, the rate at which current changes in the inductor. It tries to keep current steady. And if you change the rate of change of the current, that doesn't change the inductance. Big surprise. You have to change the inductor to change the inductance. Same way for voltage across the resistor, same way for voltage across the capacitor. I'm sorry, same thing for the resistance of a resistor, for the capacitance of a capacitor. Okay, I'm going to come back to this one. This one involved algebra, and symbols are hard. Let's talk about energy stored in the capacitor. What is energy? What is potential energy for electricity? What's that central formula that has potential energy in it? What is the relationship between voltage and potential energy in general in electricity? Google question C. What is the relating equation between energy and voltage? State the relationship between energy and voltage. Also called the definition of voltage. What is always true about voltage in electricity? And if you say IR, oh, state the defining equation for voltage. Okay, again, the relationship between voltage and energy, the definition of voltage. Justin's note taker, I'm already recording this, but okay. Okay, the defining equation, whoopsie, defining equation for voltage is electrical potential energy divided by charge feeling that potential energy. You can also solve this using advanced methods of algebra. You can multiply both sides by charge and say that electrical potential energy is charge feeling a voltage times voltage. Okay, I want to emphasize something. Cause and effect. This charge does not make this voltage, right? Remember this? This is test charge. The test charge feels some source voltage. Some charges make a voltage, and then some other charge feels that voltage and has that energy. Yeah, deja vu? We're going to talk in a second about what happens when charge feels its own voltage. That is to say, the charge on a capacitor creates its own pressure inside it, creates a voltage in the capacitor, which contains some energy. That's one picture of what a capacitor does. It stores energy in the electric field, in the voltage, in the pressure of the charges in the capacitor. We are going to deduce that the energy of a capacitor is not simply the charge of the capacitor times the voltage of the capacitor. Meditate upon this and get some deeper understanding of meaning of charge, voltage, and energy. as a capacitor charges up, those charges don't like to be near each other. The positive plate has lots of pluses packed in. They don't like to be near each other. Positive repel positives. The negative plate has negative charges packed together. They don't like to be near each other. As the capacitor gets more and more charge on it, the energy comes from the fact that those pluses don't want to be near those pluses. Those minuses don't want to be near those minuses. That's the essence of the energy stored in the capacitor. Now, as we just said, the foundational equation for the energy of a charge feeling a voltage is Q equals QV. The energy felt by a test charge in a voltage is the product of the test charge and the voltage. But in a capacitor, this isn't test charge source voltage. The charge of the capacitor is causing the voltage that it itself feels. So Q times V does not work for a capacitor. Every bit of charge that builds up, think about charging a capacitor from an initial uncharged state. Every bit of charge that I add onto the capacitor feels the voltage due to the charges that have already been packed in, and then it creates a larger voltage for the next charge to go on. Imagine blowing up a balloon. Every puff you make, every breath you put into the balloon increases the air pressure, right? Every breath you put in, you're having to push harder and harder against the existing air that's already in there. That's the essence of the energy stored in the capacitor. Each little bit of charge raises the pressure and pressure higher and higher and higher, makes it more and more and more energy stored inside. If I multiply the total charge times the total voltage, I will be vastly overcounting the amount of energy in the capacitor. Does it take any effort at all to put the very first atom of air in an empty balloon? No. It takes more and more and more effort the bigger the balloon is. Well, the first charge to deposit on the plates of a capacitor, it's an empty capacitor. There's no voltage if there's no charge already in the capacitor. So the first charge to go into the plates of the capacitor feels no voltage, it costs no energy. As the capacitor gets more and more full, voltage increases proportionally to the amount of charge already on the plates. The first amount of charge costs no energy. The last amount of charge is feeling the virtually full voltage of the capacitor. So it costs the full delta Q times V amount of energy. The total amount of energy stored in the capacitor can be calculated by talking about the total charge times the average voltage, or the total voltage times the average charge. Either way, you get a factor of 1/2. So write this down and think about it. The energy stored in a capacitor is half QV, V total. I want you to compare this to what we did when we talked about distance equals average velocity times time. Remember last semester? If you go at 60 miles an hour for 2 hours, you go 120 miles, right? What if you were steadily speeding up from rest to 60 miles an hour? Do you go the same distance if you were speeding up from 0 to 60? No. If you speed up from 0 to 60 miles an hour, you could multiply your average velocity, 30 miles an hour, times the time it takes. Right? Average velocity times time. Well, this 1/2 is nothing but the average voltage. This comes from the average voltage. We start at 0, we end at V final. This average voltage is V over 2 times charge. If I multiply just total charge times total voltage, I'm double counting the amount of energy stored in the capacitor. When do I use 1/2 QV? I use 1/2 QV if and only if I'm talking about the energy stored in the capacitor. The total energy because of the total charge of the capacitor, 1/2 QV. In any other circumstance, if I'm talking about a charge in a voltage, QV. Capacitor, half QV. Individual charge in some voltage, QV. Is good? Question.
Like the whole, or was it the
Capacitor, just a capacitor,
but just, and then the
QV. QV in general, if I've got a charge Q, it feels a change in voltage V, the energy lost or gained by that charge is Q times V. But if I'm talking about some charge that flows onto a capacitor, builds up on the plates, develops a voltage, the energy that it took to charge up the capacitor, or the energy that you can get by releasing the charge from the capacitor, half total charge total one. Do not, I repeat, do not just see there is a capacitor, throw in a 1/2. We have to be talking about the energy stored in the capacitor, the charge on the capacitor, the voltage of the capacitor. I'm going to give you a problem in a minute where I've got a free charge floating between the plates of a capacitor. A free charge between the plates of a capacitor is not the same thing as the charge that is stored on the plates in the capacitor. If I'm calculating the total energy in the capacitor, 1/2 QV. If I'm talking about an individual charge floating between the plates of a capacitor, QV. See the distinction here? Great. Let's do some problems. As has been requested, many people have asked for more practice. So here we go. I'm going to ask you for Google Form D and Google Form E. I want you to find an expression for the energy stored in a capacitor without charge. And I want you to find an expression for the energy stored in a capacitor without voltage on the capacitor. Hint, 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 there is a relationship between charge, capacitance, and voltage. You can substitute in one expression for another using the principles of algebra and get an equivalent expression. Do this. Plug numbers in, plug letters in for letters and simplify. I will remind you that the original expression that we just had was 1/2 Q times V. And we can eliminate the Q or we can eliminate the V using the top equation. Do that. You don't have to guess. Use the formula. Plug in. Okay, turn to each other and check your algebra. I've got a lot of right answers, but a fair number of you are breaking the laws. Don't break the laws. Hey, a lot of correct answers. Principle of algebra. Instead of writing a letter, you can write what that letter is equal to. If I know 1/2 Q times V is energy, and I know what Q is equal to, I can eliminate Q by writing what it is equal to. Substitute. And then I think it's ugly to write CV times V. I greatly prefer to use the idea that if I multiply a number by itself, that's called squaring. 1/2 CV squared. Now, many people got that, but then fell down on the second one. If I want to eliminate V, what I do is I solve one equation for V and then shove into the other dude. So if I've got Q equals C times V, how do I solve that for V? I divide both sides by C. As we say in Spanish, C. I am now going to take this equation and substitute it into the master equation 1/2 QV. And instead of writing V, I'm going to write what V is equal to, Q over C. I think it's ugly to write 1/2 times Q over C. So I'm going to rearrange that to Q squared over 2C. Please make sure that you can do this level of algebra. Please turn to your neighbor and review what just went into this. You're going to find that sometimes this version, that version, or the other version is more useful for any given problem. You can do it in 2 steps, but here's how to get directly to an answer. Okay, take a second and then ask me a question. You mean here?
Yeah.
So do you agree that where 1/2 if Q is equal to CV, then instead of writing 1/2 QV, I could write 1/2 CVV. Q is equal to CV. I mean, there's a V in this expression and there's a V in this expression. There are 2 V's. Yes, there are. If I have X equals 2Y and Z equals 2X, when you plug in, you got 2 times 2 times X, right? Or 2 times 2 times Y. You can't say, well, there's already a 2 in this expression. When I plug in CV in here, yes, there's already a V in here, but I'm not double counting. I've just got 2 V's, V times V. Question me, Jane. Sure.
Basically, just if A equals B, B equals C, A must also equal C.
That's right. That's right. This is algebra. This is algebraic substitution. If two things are equal, if something is equal to something and something is equal to something, then you can plug in. Absolutely, positively. Okay, you will use one version or another of all of these formulas in various problems. I am asked from time to time, well, which one applies? Whenever I've got a capacitor, all of these equations apply to that capacitor. How do you know which equation to use? What are you given? What do you want? Look for an equation which combines these things. If I ask you for charge and tell you capacitance and voltage, what equation would you use? Well, I'd use the equation with charge, capacitance, and voltage in it. If I'm asking you for energy and give you capacitance and voltage, well, I'd look for the equation that's got energy, capacitance, and voltage in it. Multiply those up, divide by 2. When in doubt, you can do this in 2 steps. You can use Q equals CV and U equals half QV separately. If the algebra is wrecking you, then I give you permission to use these 2 equations separately. But if you can apply the algebra in here and substitute in and get the other forms, you could do problems faster in 1 step. That said, let's do a problem. Let's apply this to a practical problem. Tell me, how much energy is stored if I've got 100 microfarads and 12 volts? These are terribly practical values of voltage and a filter capacitor. Hey, what's a micro? Remember what micro means? 10 to the minus 6. Micro million. Hello. Squeeze me. When you are in doubt, use the formulas that were just on the board. All you gotta do is plug in. Hmm. 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 Okay, so the formula which relates the quantities requested and involved here is the energy equals 1/2 capacitance voltage squared. The capacitance of the capacitor is 100 micros. The voltage is 12 volts. 12 squared is 144. Divided by 2 is 72. So I turn this into 7,200 micro, or also called 7.2 milli, or 7.2 10 to the minus 3 joules. Any of the ways of saying it are equivalent, or 0.0072 if you wish. Hmm. Hmm. This makes you unhappy. Hmm. Well, tell me here. Arrange this. Shuffle the formulas here. Google form G. Can you find the charge that is stored on the plates of the capacitor? Find charge in this example. Bye. Oh, don't go. Okay, better. I use the formula charge equals capacitance times voltage, the definition of capacitance rearranged, and I get 1.2 millicoulombs, or 1.2 times 10 to the minus 3 coulombs equivalently, or 1200 microcoulombs. Ask me a question. Google Form H. A quarter of the class, I feel, is really struggling at this point. So a quarter of you asked me a question. Show me where I'm confusing you. Where you are stuck, or as my 2-year-old says, where you are guck. Google Form H. I've only got one more thing to do after this, but I'd really like this to make some kind of sense. My day sucks. Thanks for asking. But not because of y'all. Q represents charge. Yes, Q always represents charge. If you've connected the capacitor to a battery, yes, the charges come from the battery. If you connected the capacitor to a power supply, yes, it comes from the power supply. We have applied a current to the capacitor and charged it up. That's where the charge comes from, yes. The difference between the capacitor formulas. They have different variables in them because we've solved for different variables and plugged in. They're all representing the same thing. Half CV squared, half QV, Q squared over 2C. It's all the same. I've just plugged in the definition of capacitance in to eliminate one variable or another. Biggest struggle is force versus electric field. I'm going to say we could do that, but that's not what we're struggling with today here. Potential energy is joules. Yes, all forms of energy and work are always joules. Joules, 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 joules. Mixed up charge and energy. What's the difference between charge and energy? Experience, practice. Do stuff in physics and think about what you're doing instead of just letter alphabet soup. Interpret these things. And if you are not sure how to interpret, then ask. You could email me and say, am I thinking about this correct? Okay, why is it Q equals C times V and not U equals Q squared over 2C? Both of those formulas are true statements, and you can use them in any order and in any combination. If we're talking about capacitors, charge on the capacitor is always capacitance of that capacitor times the voltage across that capacitor. Energy stored in the capacitor is charge on the capacitor squared divided by 2 times the capacitance of that capacitor. Those are both true statements. Why do I use Q equals CV instead of Q squared over 2C? Because it's easier for me to just multiply those two numbers, but the other way would get you the same answer. Since voltage is energy per charge, why do I not just multiply energy times charge? If you divide this energy by charge, you don't get the 12 volts voltage because of what we just did for a quarter of the class. The energy stored in a capacitor is not just the voltage of that capacitor times the charge of that capacitor. Review what I just told you. You'd be double counting if you used all of the charge times all of the voltage. In a capacitor, 1/2 times charge times voltage. Could I list all of the names and the units of charge, capacitance, voltage, and energy? Sure, why not? Q, charge, measured in coulombs. C, capacitance, measured in farads. V, voltage. Hopefully you remember this one. Measured in, you'll never believe this, volts. U, potential energy. Measured in always joules. Capacitors is a storage tank. As charge enters the capacitor, voltage goes up or stays the same or down. The more charge you have, the more energy, the more voltage. Q equals C times V. As Q goes up, V goes up. The difference of the capacitor formulas. They have different letters in them. You use the capacitor formula that has the letters that you have to get the letter that you want. Okay. I hope that some of that makes some kind of sense and is some kind of useful. There is one more problem, one more thing to give you today. I am going to give you a formula. Question first. W. That's how I write it anyway. Okay, so I'm going to give you a formula here. You may recall from last semester that energy is conserved, and unless I have an external force doing stuff, initial energy equals final energy. The electrical formula for energy, unless I'm talking about a capacitor's total stored energy, is just charge times voltage. Kinetic energy, I'm talking about speed in this problem, is half mv squared. Hopefully that tickles some neurons, triggers some memories here. So if I write stored energy releases, and if I start with some kinetic energy and some electrical energy and release that into purely kinetic energy, I could just write half mv initial squared plus charge times voltage equals half mv final squared. Please note V and V are different terms. When I multiply Q times V, I'm talking about voltage. When I multiply half mv squared, I'm talking about speed or velocity, magnitude of velocity. I write my speeds or velocities as lowercase v's and my voltages as capital V's. Beware. For the sake of brevity, I will solve this equation and then we'll discuss it for 2 seconds, and then I'll take questions and release you, like a capacitor like an electron from a capacitor. To solve this equation, I'm going to undo order of operations. I'm going to subtract off QV and get rid of M on 2 and square root. Their results I challenge you, particularly if your algebra is shaky, do this yourself. Be able to rearrange a formula and solve for a variable. Okay, now let's take just a second and talk about whether to use positive or negative charge in here. I'm going to give you a problem in a moment where I have an electron speeding across the gap, smacking into a positive plate on the other side. If the electron is pulled from the negative plate to the positive plate through that gap between, is it speeding up or slowing down? Google form. Is an electron speeding through between the negative plate to the positive plate? Does that speed up or slow down? Google form I. Did I say speeding down or slowing down? Does an electron going from the negative plate to the positive plate speed up or slow down? Google form I. I'll encourage you to think about whether electrons are positive or negative and whether opposites attract or repel. Again, my question for Google form I, half second. My question for Google form I is if I take an electron and let it go from the negative plate to the positive plate, will it speed up or slow down? Question in the backup? Okay. Okay, time's up. The correct answer is a negative particle is going to speed up as it goes towards the positive plate. Negative things are attracted to positive things. So in a second, I'm going to give you a problem where the charge on the test charge is negative as it goes towards a positive voltage. It's going to speed up. In this equation, should the initial velocity be bigger or smaller than the final velocity? If I've sped up, did I start faster or do I end faster? I end faster. My initial should be smaller. If I have V final squared minus 2QV, does it make sense to plug in a negative charge for the electron, or should I take the magnitude? What is going to give me smaller initial? Do I want to subtract a positive or do I want to subtract a negative number? Again, if we have reasoned based on logic that the electron speeds up as it goes across. It must have started slower. What do I need in this expression to have a smaller v initial? Do I want to subtract off the positive or subtract the negative number? Google Form J, tell me, do you think I should plug in positive or negative electron charge for Q if I want this to be smaller than V final? What makes sense to apply here? Am I going to plug in a negative or a positive number for Q in this equation? My answer is that if I want V initial to be smaller than V final, I can't subtract a negative. Subtracting a negative would add and make V initial bigger. So it doesn't make sense to use Q starts a negative number for Q. I should use the absolute value of charge of the electron. All right, do you have this formula? Question before I give you the next slide. Sure. What? What do you mean what it would look like? Well, I would use a negative charge, or I would subtract a negative number if my reasoning tells me that I started faster and ended slower. For instance, if the electron is projected from the positive plate and just barely reaching the negative plate or whatever. But in every case, when dealing with this, I encourage you to use, whenever you can, use logic and reasoning. Oh, it's speeding up. It must have started slower. I don't want to subtract a negative. Okay, that said, plug in numbers. I do need to give you the mass of the electron and the charge of the electron. This is Google Form K. Find the initial speed using the logical numbers. Yes. 31, negative 31. They are small. Please calculator carefully, by the way. I would also like to say that this sort of problem is why God invented scientific notation. Don't tell me as a decimal. Oh my God, scientific notation, people. Exists for a reason. Don't forget to take the square root. The electron does not go faster than the speed of light. Okay, there's some improper calculating being done. I encourage you, if you're not getting 1.1 10 to the 7, to seek resources, something to get you there. If you got 1.1 10 to the 7, good job. You can now do 3/4 of the homework, as well as most of the entire chunk of the midterm. We're out of time. I love you all. I will see you on Wednesday.